like to welcome Ronnie, Nagloo both to the seminar and today for a talk on the Painlevé equations.
Thank you. Very pleased to be speaking today. First of all, I think you all seen maybe the abstract, half of it sadly is missing. So I'm just going to say what the talk is going to be about. So the talk will be about explaining how over the past 2-3 years we've tried to use model theory to study the structure of a set of solutions of the Pentave equation. So to explain how to use model theory to study the structure of a solution set. Of Pentave equation. All right, so what are the Pentave equations? I've written a few of them here. I'm sure you've probably seen them before. So they are second order, first degree algebraic differential equations, and they satisfy the Pentave property. So this property says, so if you start with a local analytic solution, then you can extend this solution to a meromorphic solution on the universal cover of P1 minus S, where S is just a finite set of singularities of the equation.
Of the coefficients?
Right. Coefficients of the equations. For example, where T is T, for example, some of the Pentave equations, you'll have 1 upon T here, so the equation will be undefined at T equals 0, so you have to throw away these sort of singularities.
So why do you write 1 over 2y instead of making the polynomial?
That's the usual way it's presented, but you could
just have to be written rationally.
Yeah, rationally.
Okay.
Right. Yeah. So that's the form.
In terms of Y and Y prime.
Yeah.
Usually
Right.
we don't think about rational equations.
Yeah, but he did.
All right.
So you don't take into consideration, you're only looking at second order though.
Yeah, second
I was
order.
thinking of movable essential singularities.
So there are.
But there aren't any, are there in order 2 or are there?
No. So it's this definition I gave is somehow equivalent to the one that says there's no movable singularity. No.
It depends on how you define how you state the Painlevé property.
Yeah.
He didn't think so.
Yeah.
But a lot of people do. So there are very couple of different ways of defining Painlevé property.
One of the difficulty with the notion of movable singularity or not is when people use it, they don't make clear what they mean by solution.
Absolutely.
Whether they're talking about general or whether it's about particular solutions. Whereas so now it's accepted that instead of using this definition of extending to meromorphic solution and universal cover, and all the Pentave equations satisfy this property.
Order less than 2 has no movable essential.
Yeah.
But 3 does.
3 does, yeah. There are examples of.
Yeah. Okay. Yeah. So you take that definition.
Yeah, we take that definition. But this is not what the talk is about to characterize Pentave. Right. It's a question whether there are algebraic characterizations, differential algebraic characterizations.
Yeah. Order 1 there.
Yeah. So order 1 there is Alexander Buhm as well. Buhm did some sort of generalization that works for algebraic D groups, but beyond that they are. Yeah. Okay. Right. So what is the question? The problem we're interested in here is the following. So let y1 to yn be a distinct solution of one of the Pentave equation. So So we want to know whether is the transcendence degree of a differential field generated by the solution of a city is 2. So whether the tuple y1, y1 prime, yn, yn prime are algebraically independent over CT. All right, and so this is a natural differential algebraic question, but also it's related to some problems in model theory about classification, which I'll talk about as we go along the talk, right? Yeah.
What do you mean by distinct solution?
So that's the next thing. So what do I mean by solution? So usually people think of solutions as meromorphic functions on a little domain, but for us solutions will be just points of a differential field extension of CT will be by D.
Distinct means you're not going to just add a constant.
Sorry?
Distinct means you're not just going to add a constant to get it.
So there are easy. So when so that's the point with the Painlevé equation. There are easy cases where.
Look at transcendent degrees.
Yes.
Sorry. Yeah. So there are easy cases where this is
equal.
not even going to make sense because they are, for example, order 1 subvariety. But for the general Painlevé equation, and we shall see, this stated like this is enough, because distinct solutions already... yeah.
So you're not sticking to meromorphic, you're sticking to any...
Any. But
yeah.
I'm going to also put more assumptions, like we'll work in a
Because that's what
universal...
Painlevé really wanted,
Yeah.
not just... Because he objected to Sonia Kovalyevsky's following Drashvest.
Yeah.
But that's good. That means he said he does not want to put on the solutions any particular properties of solutions in a complex analytic sense.
Yeah, yeah.
So I thought that's more in the spirit of differential algebra and model theory.
Exactly, yeah.
Yeah.
All right, so this, and so, as I say, there are obvious cases where this is going to fail, and we're going to see that. But also, the only general result that there was before the work with, by the way, part of this is joint with Anne and Billet, and before the work there was Nishioka, so Japanese mathematician, who proved that for P1 this is true. All right, and so he doesn't use model theory. He uses differential algebra and calculations and heavily relying on calculations to get that. And so in this talk, I'm going to talk about the generic Pentave equation. So this is true of the general Pentave equation. And so what do I mean by generic here? So generic just means that, I'm just going to say, all the parameters, generic, just say generic P2 alpha P4 with the relevant parameters, same time, and P5. So by generic, I mean that the complex parameters are transcendental, and if there are more of them, they are algebraically independent over Q, right? And so, and I'm also going to talk about a weaker. So that's a weaker form is true of P3 and P6. So Anand, probably 2 years now, gave a talk about the Pentave equation, and he proved what's called geometric triviality. And so this is important in trying to solve these questions for these equations. And I'm going to recall what Anand talked about and try to give a proof of how one can show that this is indeed true of a generic equation. Okay.
Just so I have it straight, saying it's true means that for every n and for every set of n distinct solutions.
Yeah. So, and of course, so we're going to see that for the generic equation, this is enough, because the solutions, that as we go along, we'll see in a minute. So I'll start it. All right, so assumptions and notation. So first, U will be a big universal differentially closed field. And we assume, so we'll work there when I'm talking about solutions. We think of solution in that U. When I say differential field, I mean a subfield of our big U. And so we take a constant. Let me do that. The field of constant, we're going to choose it to be a complex number. All right? So this is just because we're working with the Pentave equations, and we want to worry about parameters coming from the complex number. And also we're going to fix t in U such that dt is 1. And notation of another notation throughout the talk, k will be the field Ct, and k node will be Q, will be, let me do that, F node T, where F node is going to be a subfield of a complex number. We're going to think it as Q, alpha, beta. Depending on the Pentave equation we work with, we are going to choose F node accordingly. All right? So, of course, we work with model theory. So we have model theory in the background. So we have fixed a language, the language of differential ring. All right? And so C, U here, is our saturated model of the CF0. And if we want to get the constant complex number, we can choose the size to be 2 to the Aleph node. So the size comes down, right? Continue. All right, and also throughout, xj alpha will denote alpha, beta, etc. will denote the solution set of the Pentave equation in U. So y in U such that y prime prime is equal to f y prime t alpha beta, depending on which Pentave equation we choose. Okay, so that's a definable set. All right. So what I'll do, I'll focus on the second Pentave equation, and almost everything I'll say, of course, except for the final result, is going to work for any of a generic Pentave equation.
So your J means
so yeah,
the particular.
Yeah, one of them. So J, where J is one of the Pentave equation. So So we focus on x2 alpha. So I'm going to drop the 2. I just going to write x alpha. Right. So a lot of properties of the Pentave equations have been known since early 80s. So people starting to work about irreducibility, about background transformation. So let me list some of the properties of P2. Right. So the first one is what's called the transcendence or strong minimality. So that's work of Umemura and Watanabe. And the connection with strong minimality, which is a more theoretic notion, came from the work with Anand. So what does that say? For alpha, not in half plus z, the following is true. For any, so because we're working with x2, f node, as I mentioned, is q.
Could you write down the equation again, please?
Yeah.
Yeah.
6 alpha plus d.
So prime is shortened for d, d by d or d. So 2y cubed plus 2y plus alpha.
Right?
Yeah. So for any f, L, differential field extension of K, we have that if y is in X alpha, then either y is algebraic over L, or the transcendence degree of L, y, y prime up in L is, so there are no order 1 element of order 1. Right. So how does that work? So let's think for, what about alpha in half plus z for a minute? So let's look at alpha is minus half. Then I claim that any solution of y prime equals minus y squared minus t up into is in x minus half. All right? So any solution of a first order equation given here is also a solution of the second Pentave. It's very easy to see. Just differentiate one more time. So minus y squared minus t equals 2 minus half, and you get back to the Pentave equation. With parameter minus half. All right, so at alpha and a half, what we have an example of solutions that fails these two conditions, right? So it's not algebraic over CT itself, and it's not of transcendence degree 2. All right? So then what do we do? It comes to the second property of the Painlevé equation. So there are Backlund transformations. So first is X so S of Y is simply minus Y. So again, it's very easy to check that if Y is a solution, if Y is a solution of a second Painlevé equation, then just insert minus Y, and you see that it's a solution of the second Painlevé equation with parameter minus alpha. All right. And the second one, T plus, which is so T of Y. It's more complicated now. It's a rational. So again, if you start with a solution of a second Painlevé equation with parameter alpha, and you insert this into the equation, you see that you get a solution of the Painlevé equation parameter alpha plus 1. And similarly, you have T minus 2 alpha minus 1.
Is there a square in the denominator?
Yeah.
No. Yes. Okay.
Yeah. And so why is this important? It's simply because we started with a solution which is, let's say, an order 1 solution here. So if you apply the Backlund transformation, well, you see that this repeats itself in all of half plus z. Right? And then to show that outside this set, this doesn't happen, it's a little bit of work. And that's the work of Umemura Watanabe. Right? And similarly, a third property was about algebraic solutions. And that's work of Murata. So P2 alpha has algebraic solution. So by algebra I mean over K solution if and only if alpha is in integer. It's an integer. All right. And furthermore, this solution is unique. All right. So there's only one. If they have an algebraic solution, it's unique. And again, it's very easy to see what happened in alpha. So let's take alpha equals 0 to start with. So we're looking at y bar prime 2y cubed plus ty. Then clearly 0 is a solution. Okay? And so again, by applying Backlund transformation, we get that in alpha plus z there's one solution. And that's the only, right? And so again, it's hard work to show that this is a unique solution and that outside this set, there are no algebraic solutions. And again, that's that's the work of Murad.
Yeah. What do you allow as Beckland transformations? What sort of transformation? That looks like differential birational.
Differential birational.
It always preserves the Painlevé property of any differential birational.
So
morphism?
differential birational preserve the Pentave property, but they are not the only one. But the differential ones, they do. These ones do preserve the Pentave property.
Yeah.
So there are many transformations that don't, and that makes things a little bit more difficult from the differential algebraic point of view. Okay, and so to put back things in context. So what was the context of this work of what's called the Japanese school? So they wanted to formalize, well, at least Umemura wanted to formalize Pentave notion of an irreducible differential equation, that the Pentave equations were irreducible in a certain way. And if you look in his work, you have that. So an ODE. So that can be taken as a definition. An ODE y prime prime equals fy y prime t with f rational over C, right, is said to be irreducible. And so that's a different notion of irreducibility. So usually say with respect to Umemura, or some people call it with respect to one classical function, or U irreducible, if and only if, coming from a translation, if you want, from the work of that we did with Anne, the solution, it has no algebraic solution. So, by which I mean in CT alg, and it satisfies the transcendence property. Or is strong, or the solution set is strongly limited. So we remember what the transcendence property was, that if you take any field extension of CT, then the solutions are either algebraic over that field, or they have the transcendence degrees too. Right.
Did you mean constant coefficients? Is this only
I mean,
rational in y prime and t, constant coefficients?
Constant coefficients.
You can't put x in there in any way and define this the same way, or
which one?
X, analytic and x and
T in T.
T.
Yeah, in T. So T.
X equals t.
Yeah, X is.
You did put t.
Yeah, I did put T here. Yeah.
But it has to be rational in t.
It could be rational in T. It could be.
Yeah, because of C of t. Sorry.
Yeah, that's fine. That's fine. Right.
Yeah.
And so.
Okay.
There was a huge amount of work trying to classify the Pentave equation according to this. And so this whole work was about determining whether the equations were irreducible. And so as we've seen, the P2 alpha is irreducible if and only if alpha is not in a half plus z union z. Because in these two sets, either it has algebraic solution or it fails the transcendence property.
I thought it wasn't reducible.
Have you catch question? No.
I was confused about the transcendence property. I thought it was a matter of not reducible to solutions of a linear differential equation.
Yes. So this.
Perhaps
This
the Being
is
variety.
yeah. This is guaranteed because
What
as I
does
say,
transcendence property mean?
so let me rewrite that. Actually, it's a good idea. Rewrite it because I have a few comments as well about that. So let me put a definition like that. And I'll restrict the set of this ODE of this form.
Thanks.
Right, so let X be solution set of an ODE of a form y prime prime plus f y prime t, so f rational C. So X is strongly minimal.
Strong minimum.
Or satisfy
That's the transcendence property.
transcendence property if for any k f differential field extension of CT either and any y in X, you have that either y is enough or the transcendence degree of f y prime of an f is 2. All right, so you don't have to begin with order 1 equations. It doesn't reduce to order 1 equation.
Right.
But also strongly minimality here is a very strong condition. It means it's not related to the constants because you have an order 2 equation, so it won't be related to the constant. So it won't be related to
the constant.
So this comes from a trichotomy theorem. So for DCF0. So there's a general result that says if you have a strongly minimal set, then it can only be of 3 kinds. Either it's going to be what we call non-orthogonal to the constant.
Oh, okay.
So there is, if you want a differential rational relation with the constant, or it's going to be non-orthogonal to Manning kernels, or it's going to be geometric kernels.
So you're using that.
Yeah.
Yes. I see.
So
that's beautiful.
because it's strongly minimal.
So that captures the whole.
Yeah, exactly. It can't, and it's of order 2. It can't be related to the constant. And so there's no linear equations.
Right. Yes.
No strongly normal.
No classical solutions.
Yeah, no classical solutions.
Okay.
Yeah.
Oh, that's nice.
All right. And so P2 is irreducible. And same, so in particular, generic Pentave equation, the second Pentave equation is irreducible. And similarly, for all the other Pentave equations, this work has been done. We know exactly where they have algebraic solution. We know exactly where they fail the transcendence property, or it's not strongly minimal. All right? And so this is perhaps where really our work started. Like, given that the generic, if you want, second Pentave equation is strongly minimal or even irreducible, well, we can use model theory because we understand strongly minimal sets in differential closed field. So let me mention the fourth property I'm interested in. So the fourth property that I looked at is what's called geometric triviality. And this was Annenstow. Well, that was a long time ago. So this is first result we had was that for alpha generic, the following holds for any y1, yn in X alpha if the transcendence degree of k naught, let me put back k naught is q alpha t, transcendence degree of k. If the transcendence degree of yi prime yj prime up in k naught is equal to 4 for all I not j. So if for all pairs, I look at the transcendence degree of yi prime, yj prime, right, is 4, then we can conclude that the transcendence degree is 2. Right? So what he's saying is, if we can show that there are no pairwise algebraic relation, then we can conclude that there's no relation at all. So this reduced our initial problem to an easier one. So instead of having to worry about trying to find the transcendence degree of all of them, we just had to look at pairs and try to answer and try to prove that any pairwise independence. All right. So this I'll talk a bit about how about the proof. It involves a trichotomy, but I won't go into details. But just to mention that, so here the results are for alpha generic. So more recently, I've been able to somehow show that this is true geometric triviality is true.
So alpha generic means you have to avoid certain alphas?
Sorry?
It means you have to avoid certain alphas?
Yes.
Generic, I mean, if you take a transcendental constant.
Yeah.
Any transcendental constant.
Yeah. Certainly can't be a half plus c.
Yeah.
Can be algebraic?
No, so that's what I'm saying. So that's recently I've been able to show that holds for all alpha not in a half plus z. So everywhere where it is strongly minimal.
That's nice.
So being able to extend. Right. So if at the end there's some time, I might just say a few words about how.
So it's more general.
Yeah.
Yeah.
But this is only for the second Pentave equation.
Okay.
For the others, it's a bit more complicated because generic parameters are, we don't even have to look at the actual equation. Whereas for the other parameters, we have to somehow look at the equation. And so the Pentave 2 is not too bad as an equation.
So, just maybe a silly question.
Yeah.
So suppose I have suppose I have one solution y, which has transcendence degree 2.
Yeah.
Now, I could easily cook up different copies of it somewhere else, right? So then the two of them would give you transcendence 4, right?
Cook up in
Well, somewhere totally disjoint from this field. And isomorphic copies.
Yeah.
Can I do that? I mean, I'm in a universal field, right?
Yeah.
You're taking a linear disjoint and then.
Yeah. So what's
So my question is, so that means that I could call as many ends, as big a sequence of solutions like that as I want.
Yeah.
Is that correct? Satisfy this property?
Yeah, you could. But it's not guaranteed that if for an arbitrary alpha, if I take n solution, I will always have 4 here for pairs.
That's what you say. You can't
No,
do it in 2n. transcendence to
No,
create.
no, I give you alpha generic. Alpha generic is fixed.
Yeah. Yeah, alpha generic, yeah.
So I pick a solution,
Yeah.
one solution,
Yeah.
and then I cook up copies of it somewhere else, and
Yeah.
keep picking copies so that I would have degree 4 for any two pair, right?
Yeah, which is fine.
Yeah,
Yeah,
which is fine,
which
right?
is fine.
That's enough, you say.
Yeah,
You could
yeah.
group them.
So it's enough. So we don't have to go about trying to prove independence for more than pairs.
Yeah.
Okay.
Why
So-
can't you do your thing?
No, I'm just saying that, so let's say you have y1 and then you have y2, and this says that I really cannot find anything that is algebraic over y1, y2, and y1, y2 prime, which would be a solution and still satisfy that transcendence degree. No matter how I try, I can't.
Yeah, because it says for any y1,
Yeah.
yn.
And so you can do that even in the universal field, you're saying.
Yeah, that's an interesting result.
Okay, all right.
And so
It's very strong.
Yeah.
how did we?
You're assuming that it's true for pairs. You're assuming.
Yeah.
Yeah.
You're assuming that it's true for pairs.
Yeah, I assume that's true for pairs, right? But I could keep going up, and you're saying that every time I really cannot
Then the next result
find a solution
precise. It isn't what happened.
which is kind of dependent on the previous
Yeah.
one that I've tried
Yeah.
already.
All those are homogeneous.
Even if I am in a universal
Yeah.
field.
The ones where alpha's in one half, let's see.
Different algebraic groups with different alphas, or is
Yeah.
it somehow related, or what?
Yes, they're all related.
Related.
There's the risky dent to mess up too. It's the lax pairs. It's not.
Oh.
Yeah.
Fine.
That's nice then. I like that.
And so how did we prove that? Basically, so let's forget for a while that we knew that, and we knew the result. So with this ideas of proof. Okay, and so as X alpha is strongly minimal, we have the following. Either X alpha will be geometrically trivial, or X alpha will be, let me put it, closely related to EA sharp. So where EA sharp is what's called the Manning kernel. So closely related here, we mean in model theory, we mean non-orthogonal. So there's just a differential rational relation, maybe defined with extra parameters between the two sets. And so an example of E sharp was if we take the elliptic curve x squared equals y minus 1, y minus t, then it's well known that ET sharp is simply a 6 Pentave equation with parameters 0, 0, and a half. So E sharp is simply,
Zero.
yeah, 0, 0, half. I must say, Manning kernel of an elliptic curve. Not defined over a constant. All right, so what is Manning kernel? It's simply the Colchin closure of a torsion point of that elliptic curve. So if you start with an elliptic curve, we will have the Colchin closure. So that gives us the Manning kernel. All right, and so this is, of course, not a trichotomy, it's a dichotomy. Simply because, as I mentioned, non-orthogonality preserves order. So if two things are non-orthogonal, they have to be of the same order. So, or usually you have to have a trichotomy, so either it's the constant, but because they are, if it was non-orthogonal, they have to be the same order. That doesn't work because the constant is order 1, whereas the Pentave equation is order 2. Similarly, here we reduce to elliptic curve because examples of Manning kernels of order 2 comes from Manning kernels of elliptic curve. All right, and so I won't explain, say more than that. But the idea is that this is if we, as soon as we have Pentave equation and we know it's strongly minimal, then it's either these two. Either you have this binary relation, or you have that it has to be non-orthogonal. And so the proof consists of showing that this can't happen. So you just show that there can't be, it can't be non-orthogonal to, it has to be orthogonal to Manning kernels. And so that was Annan's talk, and I thought I wouldn't talk about that again. Maybe I shouldn't have.
So excellent.
Probably should have said a few words about that more.
So it's the third Manning kernel. Manning kernel for this.
Sorry?
It's the third alternative.
No.
No, yeah,
No.
third alternative. So,
For this
all right, let me say the trichotomy how it looked like.
Yeah, Ronnie has a different rational map from the elliptic curve
So
onto
let-
Pentave sixth.
X be a strongly minimal set.
Yeah. Oh, yes. Okay.
So by which I mean every definable subset is finite or cofinite. There are other ways of characterizing it, but so general order. Here we have a strong minimal set of order 2, but here of any order. So then either 1, x is what we call non-orthogonal to the constant. 2, x is non-orthogonal to the Manning kernel on an abelian variety. Not over the constant. Or third, it's geometrically trivial.
Painlevé 1. No parameters there.
So, in general, the trichotomy is that, but because the non-orthogonality preserves order, we can reduce that to these two cases.
Oh. So if you had an elliptic curve defined over constants, and actually I take the local equations,
Yeah.
constant coefficients,
Yeah.
then if you look at the logarithmic derivative, then if you look at the kernel of that,
Yeah.
then that's 1.
That would be 1.
Well, it'd be 1.
If it is strongly minimal, that's the first.
The constants are.
The constants are, but the logarithmic derivative, the solution has to be strongly minimal. So you must not have any.
No, I was thinking of the analog of the Manning kernel for an elliptic curve defined over constants is the.
Yeah,
That's
exactly.
the constant trace of the elliptic curve.
Yeah.
And that would be 1. So you're taking care of all 3?
So it will be 1. They give some
that's strongly
non-orthogonality.
minimal.
Yeah.
The proper varieties are either,
Finite sets or.
finite.
Or
cofinite. Yeah.
Cofinite.
Yeah, okay.
Yeah.
You say, what's the word after variety then?
So not over the constant. So you would want to say of C trace 0 or not over the constants.
Yeah.
Not.
No. Yeah, it's stronger than just.
Yeah. So you should say.
It's isomorphic to a constant
Yeah.
variety over a lifted field when you lift the base.
So the proof really is to try and get rid of this case. And so, so I'm not going to talk about this today. So I'm going to rather talk about how we use geometric triviality to get to our main problem of transcendence. Right. So So remember that, so to solve our original problem for B2 alpha, all we need, where alpha generic, all we need to do is to prove a thing. So we need to show that given y in x alpha, there does not exist z in x alpha, z different from y, such that z is in k node y, y prime h, right? So all we have to show is that if we take pairs of elements, if we take an element, there's not an element which is algebraic.
Why can you only do it for one field?
So the idea again is, if you geometric triviality again. So once you have strong liminality, there's quite a few important things. So if it's geometrically trivial, it can't have any relations to a constant. So proving it over k node is the same as proving it over k.
Any field L. You're supposed to do it over any field, right?
No. So my original question was over CT. We want to prove that there's no algebraic.
It's still over any extension L. I thought you said no.
So geometric triviality.
He's looking at.
Yeah, okay. I'm looking at the original question where we want to prove over CT that the transcendence degree is 2n. All right, and I'm saying all we need to prove over k now.
All right.
Right.
Yeah.
Okay. So let me state as a proposition. So let alpha not in QH, so generic, then x alpha is, I'll say the word strictly disintegrated over k node, so which is to say that if y1, yn are distinct, then the transcendence degree of, let's say, k node y1 prime yn prime is 2. Right? So that's the statement we originally wanted. I'm just writing it as a proposition. Okay? Over k node.
Strictly disintegrated. Okay.
All right, so we're going to look at the proof. Try to do a rather good sketch of the proof this time. So now model theory is going to appear a bit more. So proof. So let y be x alpha. So remember, we want to show that there are no z. So suppose contradiction that there is z in k node y y prime alg, where z not the same as y. All right, so say fz is 0, where f is q. I write it, it's k-note, but I'll write it explicitly. Right, so, sorry. Should have y prime. So this is the minimal polynomial. And so what we do, we write it, so we're going to use logic, so we're going to write fu equals 0 as a formula so phi u v u1 v1 is another formula. All right, so we are explicitly say that in this formula y alpha t appears. Right. So then the following is true.
You don't really want to switch the variables?
So you mean the y prime?
Yeah, where's y prime?
No, so because in the formula you have d, so in our language we have
okay.
0, 1,
okay,
plus,
okay.
minus.
All right.
We have also a d, and multiplication sum. So it's included in our variable. So we're just coding it this way. Right? So the following is true. So there exists a u such that u is not the same as y, and u is in x alpha. So this is, I should formally write u prime ud, the formula d, d square u equals 2u q plus du plus alpha. But that's a shorthand for that. Alpha prime is not 0, is 0, sorry. And u y alpha is true. So now, note, x alpha is irreducible. So remember that means no solution in k alg, k not alg, k alg, and strongly minimal or satisfy transcendence property. So this means that any solution, any element, let's put it this way, every element of x alpha satisfy the same L formula with parameters from k nodes. So for mole theories, that's not very difficult. We have only one generic type, and so this type is determined by the equation defined in the Pentave equation. So they all satisfy the same L formula with parameter of k node. I don't know if there's an easy way to try and make that obvious for people who don't know much more theory.
You didn't say that. You didn't say that there's only one formula. So of course.